Okay, I hope you guys can see the screen, correct? Can you see the screen now here? So, okay, last time I think one point of the PCA I just forgot to explain. It's like we have already gone through all the points, but just to mention you this point, just revision. Okay, then we will go with the week 2 one point also. That is very important point. Okay, so what we have seen last time, like we know now the graph, we know these. You guys can see that, correct? The graph. I can't. Oh, thank you. Okay, so we know that this is okay. This is for example height, and this is your weight. Okay, and you are just trying to see which line represent this best, so you just mention this is the best line because these are all linearly placed. These points are here, all are like along this line the points are there, so it's best to represent that points means this line passing through the origin. This is the best line, and what you did, you just put the proxies on this line, and finally you got, oh sorry, this is not perpendicular, but yeah, the concept is perpendicular. So finally, here this point, this uh, so for, yeah, this is x point, and the point here is nothing but c, because this line is represented by some w, so c into w, this point c into w. So c is what? C is your 1 over n x into x transpose, and then w is what, you know that, right? Sorry. Hmm. This error, this error here, this one, you are okay. For example, this point you mean to say like this. Okay, okay, for example here. Oh, okay, so here, here. Hmm. So these are the projections, projected points. So point, actual point is here, this is actual point, and you, this is called as projected point. Okay, this is projected point, projected point on L1, projected point on L. For example, if it is L line, so this is a projected point. Okay, so this projected point is like, you don't want anything in the air, you are just projecting it on the line, so that is projected. So this is called projection, and this is called a projected point. And this is what, so we know that this is all are like w, because the line passes through, for example, 1, this is 2 comma 1, 2 comma 1, this point. So you are just passing the line through this point and origin, so that is line is L. But what is this point? This small point is called w. So if I want to get this point, because you know now this line is having some kind of equation, y is equal to mx, c is there plus c, but c is going through origin, so c is 0, correct? So correct. So now the relation is like 2 comma 1 means x is 2, y is half of the 2. So if I go here, if I go here, so here maybe 4 comma 2, this may be 4 comma 2, correct? This may be, if I go here, it is 6 comma 3, correct? So if you know the first point w, like 2 comma 1, and you are just multiplying, next point will be 2 into 2 comma 1, 2 into 2 comma 1, like 4. Oh sorry, I should write the straights, because people are later on, students will give me the comment like you should write straight here. Okay, so 2 comma 1 and multiply by some value 3 here, so it is 6 comma 3. Okay, so next point, what, next point is same way, but like you are just multiplying that c, that is considered as a c, and this is considered as a w. So that's why I mentioned this point as a cw, because you don't know what is the scaling factor here. That's why we mentioned C, and the point is W as it is. So you have to calculate this C value. What is the C? Because W, anyway you have the W value here, you have every time W value, and you have to just calculate your C value. So that's why C is like what we X into X transpose, like this, what we mentioned here. Okay, this one. So I will just draw one more time because this point is important. Okay, so what we mentioned like last time, this is maybe here, I'll do fast little bit. Okay, these are the proxies. So what I am doing, so this is your height and this is your weight. Okay, so we know general. Okay, in general what we know, like if somebody has more height, his weight is also a little bit more. So like more, they have like a linear relationship, height more, weight is more, height less, weight is less. This is something we know, the generic point. Okay, so in this case what happened, these proxies we drawn on this line here, because this relationship we found that this is a linear relationship, we draw the proxies on this line. So in the next point, once we change the height, if I consider, take the height here, take this height, because it's a linear relationship. So if I just increase this height from here to here, if I increase the height here, this height, the weight is also increasing, correct? So as height increases, weight is also increases, means they are dependent on each other, the points. This x1 or this feature is depends upon this, like y is dependent upon x, this y is dependent upon x. But what is now we will do here, what we'll do, because we mentioned this as a one W value, because you know that W is earlier I explained 1, but later on we consider it should have the unit length. Unit length means this value should be like proxies of W square, the norm of W should be 1, means this point is considered, because we have to normalize this, so under root of 2. Okay, this should be this point, or this W is considered as 1 comma under root of 2 and 1 comma under root of 2, this W. Okay, so what we did here, that W, this line passing through the origin, and we are putting all the proxies on this, and we found that if your height increases then weight increases, means this is a linear relationship. Okay, so the point what we want to see here, instead of height and width, this graph, instead of this height and width graph, if I simply, let me instead of the height and width graph, if I create another graph which has height plus width, sorry, height plus weight. Okay, height plus weight, because this is what I am doing is I am just multiplying with this W, height into root of W, weight into under root of W. I just want to plot this graph. Okay, and same way here also, height plus weight divided by under root of 2. Okay, so if I just simply make, this is something important point. Yeah, like I want new axis, instead of height axis x and weight axis y, I am taking height plus weight divide under root of 2. So I'm just multiplying that to under root of 2, because we know that we consider earlier this W should be unit length, because we are interested in this kind of unit vector. So you are just trying to see that whatever the directions on this unit vector, so you are interested in this W which are on this unit vector. You are not interested something outside this here, because we are considering only the unit vector. That's why, for example, if I am doing height plus width divided by under root of 2, if I am having another x axis, height plus width, and here what, height plus width, here. So this, because this is x axis, so this side is minus, so minus height plus width, not width, height plus weight, because this h into w, I every time consider height width, but here is height and weight. Okay, because this is y direction, so minus height and weight, so consider like this, and this is height and weight. So what happened, I am just now trying to draw the new axis, height plus weight by under root of 2, and here height minus weight under root of 2. So if you see the same point, the whatever the points I am here I am doing, so if I just plot the same point, this point will be something here, this point, because all the points will move here, these points will come like this. So whatever now these points, whatever I am just showing these points, because this is a new axis, so height plus weight divided by under root of 2 if I do. So I am just projecting now, instead of this way, this line, I am just rotating this one here, and if I just do this like this, height plus weight divided by under root of 2, if I have the new axis, height plus weight under root of 2, all the points will be these, all the points, like whatever the points I have drawn here, these points, okay, they are like coming like this way. Just consider this axis, for example, just visualize this line, you are just dumping on here, on this x axis. Okay, just you are changing this angle, putting it all this on the x axis like this here. So this I am just drawing at this point. So if I point like this, so what happened, this axis height plus weight under root of 2, this axis is, because earlier this graph is 1 and this graph is 2. Okay, in one graph we saw that as height increases, weight is also increasing, means there is some relation. But here if you see, height plus weight under root of 2 divided by under root of 2, because this is new x axis, if I just increase the points, there is no effect on this, there is no, because if you are doing like this here, this should go up also, no? So that's why this graph is minus height, because this is like negative sign, minus height plus weight divided by under root 2. So if you see that, if I just increase this height plus, if I introduce new point, so it is coming on this line, but nothing is coming here, like it's not giving any information about this point, height plus weight and minus height plus weight under root of 2, it's not giving any information about this axis, it is just giving the informations about this. And what is this line? This is called L1, and or what is this? This is called principal component 1, because this is your principal component 1. You are trying to get more and more informations from the eigenfaces, what we have seen, that phase detection. So you are trying to get more and more informations from that image in this direction. Whether I have more information, so try to get more and more information, try to get more and more variance. So I am getting more variance or more eigenvector values or more variance value from this L1 or principal component 1. Okay, this line. So I am just putting the same line here, height plus weight under root of 2. Okay, this line. So this is principal component 1. But what happened? What happened to this PCA 2 here? Because if I want to get another, if I want to draw then another principal component, which is, sorry, if I want to draw here another principal component in this direction, because they are perpendicular, we know that this line is, for example, L2 here. Okay, L1 line is here and L2 line is perpendicular to this. So if I want to draw L2, this line will be in this direction, so I will get more information in this direction, but that is different line. L1, this is PC2, principal component 2, principal component 1, because we know that L1 line is giving more variance in this direction, and we call this one as the line L1 or principal component 1. Okay, and that gives more variance along this direction of the input. And next is line PC2, which is giving another this direction, which has the different variance of the same image but in this direction. So there is no relation, like in this graph, if you have seen this graph number 2, you have seen that if I just try to get more variance, I will get the variance in x direction, this direction. There is no more variance or no more information in the y direction, because this is different. So this principal component 1, if you just simply get principal component 1, you will only get the more variance in that direction. There is no informations about the variance in the other direction, line 2 direction. So that's the reason you have to calculate PC2 also, principal component 2. Okay, so these whatever you are now finding, so in PCA, what PCA do, the PCA finds the combination of the features that are totally decorrelated. Like these features are here these directions, you know, these points. Okay, I got these points which are in this direction, but they are not having any impact in these directions. These points are not giving any informations in these directions. The face of, we have seen like different faces of the people last in PC1, PC2, PC5 also I have mentioned. So the person's face here is not the same. Like whatever person face you will get the same person it, but in another directions you will get the person's face here. Like more informations, more variance in that directions will be added in this face, which is not present here. So with this reason you should not stop at one PC1, you have to do calculation of PC2. So you will get more and more variance informations, more and more informations from that object if you go more and more, if you calculate more and more principal component. So what PCA doing in PCA, first time it is calculating some features in this direction, second time it is calculating the features which missed in this direction. So this direction we missed some features, okay, then okay, these directions I calculated, I got more and more features, but these directions I miss few features because this is also some kind of a data. So I miss few features in these directions, so I will calculate this direction also. So later on you will also calculate maybe another PC3 which is perpendicular to PC2 and PC1, so you will get more information in that direction also. So that this way you will calculate PC1, PC2, PC3, and these whatever the calculations you are doing, these features are totally decorrelated, like they are not related with each other, they are totally decorrelated. That's why you have to get the information from all the directions, PC1, PC2, PC3, PC4, and we will do the same thing in the principal component, what we have seen last time also and in the demo also. So here this graph means, like why I mentioned this point, because if you see the first here, the axis is x which is height, and this axis is y which is weight, height and weight. Okay, but then this new axis is height plus weight. So what happened, like sometime you will say, sir, we are compressing the data, like maybe we have like for example 100 cross 100 and we are compressing to 50 cross 50, means we are are we just discarding this data? No, we are not discarding the data, we are taking the data also, but we are giving less weightage to the data, means we are creating some kind of this feature. Like you are here, you have seen like first point is height, x axis height here, and y axis is your weight, and here same way in the next point what you did here, height under root of 2 plus weight under root of 2. So you are creating the new axis. Now this is your new x axis, this is your new x axis which has the same feature points, height and weight, but they are like a scaled one. Okay, you are not dropping any point, you are not discarding anything from the actual image, but you are just giving them less weightage. So you, whatever you are storing the data, that will stored into the limited amount of memory. You have less amount of, you need a less amount of memory to store the complete data. So you are giving the weightage to these features, height and weight. So your features will be the same, you are using all the features but giving different weightage, and with that one you are calculating principal component 1 here, and this way this side you are calculating principal component 2, and they are totally decorrelated. So PCA finds the combination of features that are totally decorrelated. So they are not simply calculating the PC1, PC2, but we are getting some information from that, and they are very important features, but as they are not related to each other, like whatever the feature you are calculating in the PC1, they are not exactly related with each other, they are totally decorrelated. That's why we have to get more and more principal component in practical to get the more and more informations from the image what we have, like in face detection what we did last time. So this is what last point I missed in the last session, so I just want to explain that. So any kind of questions you have here? Any question, Murli sir? Okay, this is just simple. See, these points are like for your algorithm perspective. It's not like for the exam perspective. Exam perspective, you have the now the steps of PCA. So you are now able to do the PCA calculations. But if you are going with the if you claim that you know the algorithm, so you should know these points. Like somebody may ask how you are doing compression. Are you just discarding some points? You are not discarding any points. You are still having the same points, but with some weights, like here height plus weight divided by under root of 2. So you are giving some weightage to height and weight here, height and weight. So you are giving some weightages here. You are not discarding anything. You are having same still point, but and in the next here in PCA, in principal component calculation, your actual features are changed. Like you earlier used, for example, here height only, but now is height plus weight. So the features are also like change, but we are not removing any, we are not discarding anything, but we are just creating the combinations of that. We are creating new features, like the feature x, capital X, which is nothing but height plus weight in divided by under root of 2, something like this. So in these directions you will get more and more variance here, and if I calculate PC2, I will get more and more variance in this direction, y direction. Okay, so I have actually this time I have created this this notebook for you to have this idea. Okay, so here, because as I mentioned last time, the same way you can also I have my git repo for this. You can access that later on if you want to also do some kind of work test on this one. So here, as I have mentioned, this is what because this week 2 what sir has given, sir also started with the same example of the extended L phase detection. Okay, uh, okay, before that, before showing me okay, let I will show you this point, and then I will go with one basic points, and then we will start with the next point, but the next algorithmic point. But this is something I just want to finish first. So this is what we have seen last time, and this Kaggle data set. So they are having 28 subjects. 28 subjects means one subject means one person. For just example, consider like this: one subject is one person, and that one person is giving its image in different kind of lighting situations, or face, or he is showing different kind of faces, different kind of expression, and in different lighting conditions and all. So we are having total 16,380 image. This is actual image. Okay, and in lecture what sir has mentioned, so sir has mentioned we have like a nearly 20,000 images. Okay, but if you see the actual images what we are having in the data set is 16,000. Okay, and each image, okay, each image is of size 192 cross 168. Okay, if you see these dimensions here, if you see the dimension is 192 this way. Okay, and 168. Okay, one number of rows are 192 and 168 are the column. So number of rows, how many rows are there? 192 and 168 are the columns, and if you just multiply them, it's like a 32,256 dimensions. So one each pixel is considered as a one dimension. Okay, so last time you mentioned height, weight, and height, weight, and for example color. So this is like a dimensions. D we mentioned like RD is D is 3, R3 we consider height, weight, and height, weight, and color as 3 dimensions. So like this, here the dimensions are like each pixel. So 192 cross 168 is the dimension of one image. This one image 192 cross 168. Okay, these are the dimensions. So if I just really see that image, so these are the images. I just put some 25 cross 25 cross number of rows, 25 rows and 20 columns from the complete data set. I just try to show you that how these data set looks like. Okay, this is what the complete data set of the EL extended AL phase detection data set. So if you see like here, so here the A1 2 3 4, these what I have shown, these 5 images is from this 1 2 3 and 4 here, these 5 images. So if you see that there are different kind of face grayscale means they are like a black and white images. Okay, they are not colored one. The input itself is like totally in grayscale. Okay, they are in a grayscale. And here what I have showed is like the complete, like some part of a data set, 25 rows and 20 columns in that data set. So you can see these are something like this. Okay, so you understood that this there are like 192 cross 168 dimensions. Okay, this 192 cross 16, so there are 32,000 256. So if I just say there are 32,000 dimensions, d cross d is nothing but one dimension is 32 cross 232,256. Okay, and I will just come to the next point also, but just want to show you this. And this is the mean phase, like I just subtracted, because the PCA, you know, now the PCA has the steps. Calculate the, firstly get the data set, calculate the mean. Once you get the mean, okay, so once you get the center, that is called as centering the data set, you calculate the mean, subtract the mean from the each data points. So this is the example of the your mean phase. Okay, that what you, after subtraction, what you get. Okay, and after, once you get the mean phase, you have to calculate the x transpose x, because we know that the C is here is the covariance matrix, and covariance matrix is the formula. We see for this demo, I use this 1 upon n minus 1, but for your exam point of view, you are considering the x transpose x divided by n. Okay, and so you are not using n minus 1 in the exam. So whenever you are doing the exam point of view for solving any kind of questions, use n minus use n instead of n minus 1 in that one, because sir has given the formula as x into x transpose divided by n. Okay, but as I mentioned you, why we are going with the why we are like actually trying to go with the, like here the formula x transpose x, why we are here the x transpose x. So the dimensions, like d value here is 32,256 here. This is the dimension, and you know the covariance matrix C is of d cross d, means 32,256 cross 32,256. That is the size of your covariance matrix. Okay, so I'll just try to, in the extended pale detection algorithm, I'll just write here. Okay, okay, so the phase detection, we are in phase detection, and here each input is 192 cross 168 image. That is, if you do the dimensions, d is equal to 192 cross 168, which is 32,256. This is your dimensions. And what is this? Your covariance matrix is actually d cross d. That is nothing but 32,256 cross 32,256. Just remember this. Okay, this is your covariance matrix in the phase detection algorithm. Okay, so we'll come to that point, but just to get the feeling here, this is 32,000 cross 32,000. This is the big matrix. So to avoid, because I can't do that this calculation with that, so for giving you the demo, I have used this trick. So I use the trick, instead of using x transpose x, okay, so I am using now n cross n, which if I do this transpose x into x transpose x to x into x transpose, if I do, this is n cross n, because n is like what mentioned, n is nothing but, how much is n? We mentioned n is like 60,000. N is what? N is your number of images. How many images I have? 60 380. These are the n value. So 16k into 16k, I can do that, like 16,380 cross 16,380, which is like consider half of this. So your computation of d cross d is this much, 32,256 cross 32,256. Instead of doing that, I am doing 16,380 cross 16,380. So that's why I am able to do it here. So this gives me little faster, the code implementation little faster, and with that I can like execute the other command. So for this example, I just showed you the little here. Oh sorry, I need to run the complete code to, I need to run all, then only I will get this data. Let me, yeah, so it will run for some time. Okay, it's run. I will just for the time being I will just go here. Okay, so this is actually what we have seen. You are able to do this extended pale detection, you get the data set, you are doing eigenphase calculations and all, but you are calculating the covariance matrix, which is the common step what we do every time. You are calculating the covariance matrix, but the covariance matrix is of d cross d, which is like 32,256 cross 32,256. So this is main challenge. So the challenge in the, okay, let me show first here and then, okay, this is 5 phases, this is here, this is eigenphase, now this is covariance matrix, eigenvalues. Okay, so here, okay, so this is the principal component 1. So once I get the principal component 1 2 3 4 5, so these are the principal components. So if you see that here, once I get the eigenvalues, okay, I get a covariance matrix. Covariance matrix C is nothing but instead of x into x transpose, I am calculating instead of these d cross d matrix, I am calculating n cross n matrix here. Okay, here this formula covariance matrix. Once I get the covariance matrix, I am calculating eigenvalues and eigenvectors here. So once for exam point of view, they will ask like what are the eigenvalues and eigenvector. You can show it till here what is the eigenvalue, but you want to get that phase, like you can't just simply put your eigenvalues there and you cannot say that okay these are the eigenvalue eigenvectors, but in your application you have to do some calculation to get back your actual phase of the image, like whatever the phase you are now detecting, you have to show that phase also. So for doing that, this is called as eigenphase calculation. Okay, so whatever your eigenvalue eigenvector you have calculated, v is the eigenvector. Okay, whatever the eigenvector you have calculated, that eigenvector if you multiply with your centered data, whatever the center you did na, x minus mean, you did the calculation, you got the centered data. So you just need to do here this calculation, u is equal to x transpose v. V is nothing but your eigenvectors and x transpose is your mean value. Once you do that, here I have done this here. Okay, so you will get the eigenphases here. Eigenphases means you are reconstructing that data, you are reconstructing that image from your whatever the eigenvectors you got it. You are just got the mean value of your input data, like you are having mean value, you subtracted it, you created the center data, and on that center data you are multiplying your eigenvectors. So that multiplication once you do, you get like this. So my first principal component I am multiplying with my centered data, I got like this. With the second principal component value PC2 I multiplied, and once I get PC1 and PC2 combined, with that both combinations if I do, I get with PC1 and PC2 I get this data here, PC2. Okay, combination of both here if you see this. So here, okay, and like this way if I go increasing number of PC3 PC4, because see I mentioned you this graph, this graph. So this PC1 is you are getting covariance or you are getting variance in this direction. So in the principal component you are getting the variance in PC1 direction. In PC2 directions, once you calculate PC2 and you combine PC1 PC2, you reconstruct the data, you get the data like this. If you combine 3 PC component, principal component, you get the data like this. Well, you are enhancing the data. See here, you are getting more and more informations about the object. whatever the object is there. You are getting more and more informations once you increase the number of principal components. But how many times you have to increase? You have to wait, you have to check like the k value, the graph what I have last time they drawn. So the k value you have to find out at what point should I stop, how many principal components should I calculate, 1 2 3 4 5 6 7 100 200 3000 4000. So for that one you have to check how much is the k value. So k value, we know that the k value is like you need to get the 95% of the variance of overall data. Like I have like complete data, and that 95%, if I get the variance from the given principal component, I will choose that principal component only. So this is the formula, like eigenvalues, and then this is the total sum of the eigenvalues. Okay, total sum of the eigenvalue and the eigenvalues what I am having here. So these calculations happen here, the k value calculation. So this value is here. So yeah, I'm just using this, I'm just actually doing the calculation here. Okay, because you don't need to go into deep into this calculation, but here this is step like choosing how many k's value you have to calculate when you have to stop. So because now I have, like earlier I used the here I can show you, here I use the 100,000 data here. I use, because as I mentioned I have 16,000, how many images I am having here is, because this is like I mentioned this data set has 16,380, but I am just using 1000 image, because if I use the complete image, the RAM from this notebook is completely filled, and then I cannot run the calculation, because the eigenvalue calculations is like a huge calculation. Eigenvalues calculation is like a more time consuming, so I need to restrict till 1000 images only. Okay, so in this case, that's why I mentioned here like 25 cross here this one. So these are like 500 images I put here. So these are the 500 out of these 1000 image I put 500 images. Okay, so what here I mentioned is like you have to get the k values, which is like 95% of variance it has to show overall, complete overall variance. So 95% is the whatever value I got is like 184. So I can calculate PC1 to PC184 images. Okay, so that is like a principal component I can calculate. I like for exam point of view you can calculate 1 or 2, that's all, but for actual project application point of view you have to check like what is the k value you are trying to get. See, like here in this case, as I am taking 1000 images, I need to get 184 principal component, that is actually the 95% of your variance. Okay, so whatever the data I got, because I mentioned you that the data eigenfaces I got, so that eigenfaces now I am projecting on the principal components. So whatever the here, so I am just now reconstructing that with the k is equal to 184. So if I do it equal to here, so the original image, and I am using all the principal component 184 components and projecting it here, so I can see the face. Both faces are like same face, but the comparison wise it is, this original is like more clear than reconstructed is not that much clear, it's like little blur, but still show the same person, same face, only the blur, because we have to compress also. So compression is also, we are achieving the compression here, and we are still getting the same, and we are able to get like 184. So as I mentioned this graph, so here we calculated PC1 PC2 only two graph. So in applications we are calculating PC 184, like this many graphs in the same graph we are calculating 184 principal components. Okay, so here we optimize this, and this gives 95% of the information. So here 95% of the variance we are getting with calculation of k is equal to 184. So this is what the reconstructed looks like. If you see, because whatever we optimize the algorithm and all, so if you go with the next course called as MLP, like machine learning practices there, so if you see there, so whatever now you implemented the algorithm, like they get the data set, center the data set, calculate the covariance matrix, and then afterwards eigenvalue and eigenphase calculation, eigenvalue and eigenvector calculation, then you have sorted it, get the maximum eigenvalues, corresponding eigenvectors, and then you reconstructed by multiplying the eigenvalues eigenvectors with the centered data, you multiplied and you got the your reconstructed data. That's fine, but once you go to the next level in the MLP and all, So there is just one library called sklearn library. Okay, scikit-learn. Okay, that sklearn library, there is like just you need to call principal component functions there, PCA, and you have to give what k you need, like 184 as I mentioned. So I mentioned that I need 184 k's. So it will internally calculate all these things. So whatever the operations we have done here, these 7 step, 8 step, and what I just mentioned you, all the steps are done with the single line here. This is all. So this is all. So that's what I want to say is, for understanding algorithm is very much important. But if you actually work on if you go outside and start working on this algorithm in R&D sections, and somebody asks you to do that, then no need to do all this eigenvalue, eigenfaces calculation. Just simply go and call the functions directly, like PCA, and you give the what are the PCA component you need. That's all. So with these 4 lines you can get the output. So if because this is what I want to also show you, what is the with the sklearn scikit-learn library, how we are doing the PCA calculation. I just did this 4-5 lines of code, and here it gave me the k value. So here I just try to get what are the k values are here, because I just want to see that. So k values, how much the k values I'm supposed to get. So this graph, what you have seen here, this graph and what we also got the earlier graph is more or less similar. So it's also giving the k is something like 184, because internally I don't know how this sklearn has developed the algorithm, because they are not doing the same way what we are doing, but their output is similar, what we are also having the same output, like the comparison things and all, and the number of principal component, what they are also using the similar way, but they are having little bit different definitions. For example, if you see in this graph, so what principal component is nothing but your directions where your maximum variance is there. So you will say this is my w1, this has direction this way, okay, passing through the origin. Okay, this is w1 which has the direction this way. Okay, and maybe in the scikit-learn they have library which has direction this way, for example. Okay, both, this is like totally flipped image. It's like one person is watching this side, okay, and one person, the next person is here in this image, he is watching this side. So this is like a totally flipped directions, like don't take as it is what I mentioned this image example, but the directions are this way, because directions does not change any kind of eigenvalues, because eigenvalues will be the same, only the w's here, the directions is changed. Okay, so that's why the implementation wise, if you see the output of both principal component things from the scikit-learn and our own output, they are not exactly looking like same here. If you see here, so this is the output. I can just show you the output here. So this output is from us, from our algorithm what we have implemented. Okay, from the manual PCA calculation, the eigenfaces are something like this, and if you see the eigenfaces from the scikit-learn, this is scikit-learn library, so the eigenfaces are something like this. So PC2 you can see something this first face here, this is PC2 here. Okay, and this PC2, oh sorry, so PC2 or PC3, this person PC3, and this person, see the PC3, this guy is having different kind of features, variance, the direction of variance is little different here with manual calculation, and inside this sklearn they are also having PCA, but their calculations of getting the principal component is the variance is little different there. The person with PC3 is here like this, looks like this with scikit-learn, sklearn, with our manual he looks like this. So they are not having the similar implementation, but like they are following the same way the steps, but in between they are having some kind of a different kind of assumptions, like we have vector w with the positive vector w, and if they are having negative vector w, they will consider the same, and they will like flip the image, and once you flip the image it will like change the appearance. So what we have seen that appearance here. Okay, so where we are here. So because this is something with the scikit-learn library. Okay, so once the same way it's reconstructing the data in the scikit-learn, and you are getting the so with the manual PCA, the reconstruction error, because as I mentioned, the reconstruction error you have to check. So it is like 88 point this one, whatever the manual calculation we did. Okay, the reconstructed image and your original image, if you see how much is that difference, like you have seen this is the original image and this is your reconstructed image, because they won't be exactly same, because they are compressed already they are compressed that. So if I just see that mean square error, so here I am getting it like 88.881912, and with a scikit-learn if I do this like 89.60. so it's more or less similar, like it's 0.2 kind of way. It's like difference, this much small difference, means more or less they are calculating the same way and getting the output. This is the output from, this is the reconstruction from a scikit-learn, and we saw that our reconstruction is here. So this is our manual reconstruction, which is here, and the scikit-learn library, whatever PCA we have calculated with the scikit-learn, their reconstruction is here. So if you see this error is like this much is, so this much means like more or less they are calculating the same and getting the output near to the same. So, okay, so this is what here I try to do the projections on the faces, like the faces what you are having. The if I am just having now, for example, I am having dimensions, as I mentioned, I have like 32,000 dimensions, but I don't want that d equal to 32,000. I want d equal to, like, now I am using for example here I am using only PC1 and PC2, so I am just projecting the data only on the two principal components. For example, okay, this graph I am just explaining. So I am just trying to project this d cross d matrix, or this much big dimension data into only on these two principal component, PC1 and PC2, and I am plotting that graph, like each pixel here, each dot is the one face, like 192 cross 168, that point. Okay, each face is that, each dot is the one face here. So how many faces we are having? So for example, we took 1000 images, like 1000 faces. So this graph is of, for example, like 1000 faces dot. Okay, so if you take more, then the dots will be more. So each point is of one face. Okay, here just I have mentioned the explanation. Okay, so this 2D PCA projection of face plot visualizations, that takes you high dimension face data, like you know that what is the dimension. This is 192 cross 168, 32,256, that much is the dimension of one image, that one data, and reduce it to just two dimension, because just for projecting that PC1 and PC2 we just projected the data, and we are trying to project that much big dimension into only on the PC1 and PC2. So this graph, so PC1 here, okay, this graph is related to our here, this graph what I have mentioned. So this is the graph PC1 versus PC2. Okay, PC1 versus PC2, this graph is somewhere this PC1 versus PC2. Okay, so this much big dimension data is just plotted here with the two dimension, like PC1 and PC2. So what we can do is here, each dot on the scatter plot represent of our 1000 image. Okay, this each dot is like one image out of the 1000 images. Okay, and the position of each dot here, I'll just try to reduce this position, and the position of each dot is determined by its score on the first two principal components. So we have like a PC1 and PC2. So we know that PC1 what is the score value, the vector, eigenvector and all, so that value, and PC2 value here. So we just plot accordingly that graph. So this is something what you can see, and if the two dots are very near to each other, here you can see these two dots, if the two dots are very near to each other, means that dots having more and more relation with each other, means the two images is of the same person, and that person's looks like the same. That's why they create one small clusters here, they are grouped together. Okay, or the principal components of that image and the principal component of another image having similar more and more common informations, that's why they group together, cluster together. And if the dots are like separated from each other, like one dot is here, another dot is here, so they are not exactly correlated, they are like a different, they are not the same person or not having the same feature. So that's why they are totally away from each other, they are not near to each other. Okay, That's why if the two dots are near to each other, they are like they are having more and more common things with each other. That's why they created the cluster of that of the two images. Dot means one image, okay, that one image. So these are the 1000 images. So the two components are the most significant directions, because we know that PC1 is the maximum variance and PC2 is less than PC1, because as we go on increasing, the variance, maximum variance or maximum informations are caught into the first principal component, okay, and later on the values are getting decreasing, like PC2, PC3, and we know that the formula last time we know that understood that if you go on next level, so then the that reduced to 0. So the maximum informations whatever you earn is in the first principal component. So in that one the PC1 has more information, so we just plotted PC1 PC2. Why? Because we try to get maximum informations plot here. PC1 and PC2 has at least the more information, like PC3 also having, but as compared to PC1 PC2 they are having less information. So that's why we plotted the first two component here, okay, and we try to get the directions of the variance in the data set. So this is something you can like I will share you this my GitHub link. You can just check that for more informations, like all the details are there. And I also try to give something like last time I showed you, so the test image. So I try to check the test image, how to if I am having different kind of a faces, how I can now project that on the principal component and get back the data. So for example here I try to get one photo as like one Virat Kohli's photo, and I try to project on the principal component. So we have seen that the extended L face has the person's face, like the person is different lighting conditions, shape and all, and different expressions. So we are trying to project this image on the that principal components. So these first 25 principal component from the data set of extended L face, I am projecting this image on this. I am trying to see, but he is not this image, he is not looks like the Virat Kohli. So means if I project on the first 25 principal component, I am not getting the data, like I am not getting the actual image. So if I increase the principal component to 50, 100 and all, so like to 150 here. So if you see now, like to the 1000, when I'm going to the maximum 1000 value, because I have maximum 100,000 images only, so that's why I can go maximum 1000 only. So if I just project that image, test image on the 1000 principal components like PC1, PC2, PC3 and all, okay, so if I do that, then somewhat I am able to generate now the person's face. This input test image, now it's generating here. So somewhat I am able to get the data from this. Like for that reason I have to go till the principal component 1000. Means what? If you are trying to detect the face, like you can say that this is human now, yeah, he is a man or he is like a human, he is not an animal or something. So you detect now this one. So on top of that now you add the SVM classifier or some other classifier, okay. So where like a supervised learning you have to add, and where it will show that this person having one label, as maybe the label is the name of the person, like Virat Kohli is the label for that. So once you get the directions here, this reconstructed data, on top of that data you apply your SVM classifier to differentiate, to classify whether he is which person, like Ashwin or Dhoni or Virat Kohli or Rohit Sharma, who is that. So depends upon that supervised learning algorithm, you can get the name of the person afterwards. So this will the PCA will give you the information till here only. It will give the information, reconstruct the data, it will create the eigen faces, that's all. So now your supervised learning will help you to get that next thing for your application, like face recognition thing, okay, whether he is that person or not, that you, for that reason you have to use supervised learning. The same way I use the another, like the image what I have shown. So this is a dog, so I am projecting that dog image onto the first 25 principal component, but still he looks like a man, but he is not a dog. But if I just increase now to 50, there are something coming here, but still he looks like a man because eyes and all something like. So once I reach till 150, so you can see the nose or some face of the mouth, something is now coming, or the eyes here is when the principal component 150, you can see the head shape is also coming, but not exactly the dog. But once I go to the maximum principal component, you can see that 200, 250, 275. I try to go that, and once I reach to 1000 principal component, I'm not exactly generating the dog face, but it is looking somewhat dog here in the 1000 last image, second row, last column. You can see this looks like a dog, but if I increase more and more, then maybe like r equal to 2000. If I get 2000 input images and run that, because right now I'm running with 1000 input images. If I take 2000, I can reconstruct that dog face, but for that reason I need to do more and more computation. PC1, PC2, PC3, all this computation I need to do. It's like once again I need to calculate eigenvalues, eigenvectors. So these eigenvalues and eigenvector calculations is more challenging. So what we understood from here, the eigenvalues and eigenvector computations or the covariance matrix, these calculations is more time complexity, like they're more time consuming data, like more time consuming process in the PCA, because we have seen that if the image is n cross n, like what we saw earlier, it's very easy. But if the image is d cross d, the features of this, because I have already implemented, that's why you are not feeling this heat here. But if I try to do the d cross d computation of the covariance matrix and then calculate the eigenvalues and eigenvectors, it is very much time consuming. It takes a lot of your RAM, of your memory, and it's not good. Like your complete RAM will exhaust, and your like system will get hotter and warm. Like that's not the good idea to do this kind of operations, or you can't like run the PCA with your normal approach what you learn in the week 1, like get the covariance matrix, calculate the eigenvalue, eigenvectors of the covariance matrix, because your covariance matrix is x into x like the formula was here, as per the formula is x transpose x, which is d cross d. So that d cross d, you cannot use the d cross d vectors here in eigenfaces calculation, which is 32,256 cross 32,256. So you have to reduce it somewhat, and for that reason you are just moving n, because here n is number of images. If the n value is lesser than d value, then that time there is another way you can calculate the PCA. Okay, but before that we found the first challenge here. The calculating the eigenvalues for the test data here, the eigenvectors and all. What is the eigenvectors? That is like the eigenvalues, like maximum eigenvalues corresponding to that maximum, corresponding to that the vectors, that is the eigenvectors. So that eigenvectors are nothing but your principal components, principal component 1, 2, 3 and 4. So calculating that principal component is very time consuming. So what is the time complexity? So you may get the questions like, how much is the time complexity? Time complexity for, okay, so the time complexity for your PCA algorithm is O into D3 D cube. Okay, this question will come like 4 options. What is the time complexity of your PCA? Okay, O into D4 or log of O into log D or something, but this answer is this much. This is your D3 cube of your dimension. So this is what the problem. So your image, if it is image of 32,256 cross 32,256, and this is D, and you are doing the cube of this, then your algorithm will be much slower. It's like, it will be like you feel like your PC will be dead or something, but it's too slow. Your system will be totally like becoming hot and warmer, and also it's your RAM will be exhausted and all. So this is what the challenge in the principal component analysis algorithm. So the first problem was this one, the time complexity. Okay, this is now the problems with the PCA, the week 2 sections, week 2 work. The week 2 1.1 is the demo what I have showed you. 1.2 is something what the problems like we are having. The first problem is the time complexity. As we have seen this algorithm now, the dimensions of the image. So in the demo I have already converted that to the n cross n. That's why I'm able to show you the demo. Okay, so if I don't convert that demo, then it's very difficult for me to show you the demo. So for showing the demo, I have converted that d cross d. Instead of d cross d, I did n cross n. That's why I showed you the demo. Okay, but on paper, on theory, if you try to see that, if you want to get the PCA, then the covariance matrix is of d cross d, which is this much, 32,256 for the eigenphase calculation. Okay, or the for the phase detection, eigenphases, or for the phase detection algorithm. Okay, this phase detection algorithm d is this much, and generally the time complexity is the d raised to 3 cube of your dimension d. Okay, for the PCA, for any example, for our eigenphase d is equal to 32,000, that's why it is cube of d. For another application d may be like huge, so that is some other examples. Okay, and the next point, the next problem, because you have every time drawn the graph and showed the graph like line L1, or like I explained you the line L1 or L2 and L3 or everything L2. Sorry, I am not able to draw it properly but yeah, L1 L2, but I explained that these all the lines are passing through the origin, and these are like linear expression, they are having linear type of relationship between these points. Okay, so we thought that L1 L2 L3 these lines are the best line. But for example, if I have I think I have this data here. Okay, I think I run this somewhere. For example, if I have the image in the 3 dimension, I just plotted the graph in the 3D. So I thought to show you GeoGebra, not here. No, not this one. Here. Okay. Okay. For example, you are having the 3D axis. Okay. So in the 3D axis, your points are, these are your points. Okay, in the 3D. Maybe copy the image. Let's put it on the okay, I don't know, I am not able to put. Okay, for example, just I will draw like here. Okay, consider I have now the example what I showed you. You are having something like points in the 3D. Okay, these are the points, and all the points are falling on this surface. Okay, all the points are on this surface only. Okay, this is 3D points. So in the 3D points, so if I draw something, these points, I'm just trying to draw it here. Okay, and these points are in the 3D, and I have like this kind of a surface. Okay, this is the surface. It's okay, like you will say that principal, I can do that principal component on this one. You can do, that's not a problem. But the main issue is finding the reconstruction error. The actual data what you are having and whatever you have reconstructed, that has a more like a bigger difference, that has a more and more error, because these points are like curve points, and also these points are like not in a straight line, they are simply in the curve one. So if I just draw something, and if I just plot, like, because we have seen that last time, this 3D surface here, the points, this line I will draw the line here, and this is what the projections of the points, that's okay, you can do the PCA here, that's not a problem. But the reconstruction error whatever you get after, because now we have seen that we reconstructed the person's face in the face detection, you calculated eigenvalues, eigenvectors there, and afterwards you got the faces there. Okay, you reconstructed the faces. So once you reconstructed the faces, you saw that the faces are more or less like, looks like the same person, correct? But here the point is, once you try to reconstruct the faces of this kind of a data which is not linear, you will get more and more error into that, because they are not having the same, they are not lying on the same line, they are, because they are distributed over this face, these three dimensions, and these are like not following the relationship equal to y, like y equal to mx. They are having maybe square relationship, a square plus b square equal to c or something. There may be something like y is equal to x square plus 5d or something. Okay, so they are not having the linear relationship of the data. So you can do the PCA calculation on this linear by considering they are the linear data, but you can do it, but the problem is the reconstruction error afterwards what you get, it is like a huge, means it's not of use to do our normal whatever we have learned this PCA. So it's not good to do these same steps calculation on this data, which is not the exact linear data. It is like they are following different kind of square relationship, like what I have mentioned, like a square y is equal to x square plus 5 or something like this, different relation. So you cannot just simply get the actual reconstruct the data from these kind of points which are like spread in the 3D. So the problem was, the first problem is the time complexity, and the second problem is if the data is non-linear, or if the data is if the data spreaded in the three dimensions which is not in the linear fashion. If the data is spreaded in non-linear fashion, how you do the PCA calculation there. So now these two main issues in the PCA is if data is non-linear, and the next point is if their dimension d, if the dimension, here in the first one, if d is greater than, if d is too much greater than n. Okay, if d is too much greater than n, means if your dimensions are greater than your number of input images, what we have seen, our dimension is 32,256 in the face detections, and your number of images are 16,000 in our case, or in sir's video what he mentioned is 20,000. So if n is, if d is far greater than your n, this case, and second is if your points are spreaded in non-linear fashion, how you will perform the PCA. So these are the two main challenges of the PCA algorithm. So that we will check, but this is something, the current more challenging thing, the time complexity thing, where d is greater than n, and if the data is non-linear data. Okay, time complexity and non-linear, these two are the main issues, or you can say bottlenecks in the PCA algorithm. Okay, so before that, anything you want to ask, because afterwards there is little math, but if you have any questions we can take it now. Yeah, Murli sir, Preeti ma'am, and Tejaswini, any questions? Okay, okay. Murli sir, anything? Tejaswini ma'am? Okay. Tejaswini ma'am? Okay, okay, okay. Because this point till point, this point, you will like, this is the 2.1 video. Okay, so that's why you may get the idea. But now onwards, this math will come now, and the actual algorithm, then you will like try your, because our brain is something like try to get which is easy. So what happen, we if we lose the track in next points onwards, then we'll just simply think about the final formula. What is the formula? That's okay enough. I am not able to, like, I'm not interested in going through the flow like this. Our mind will decide, and then it will lose the track. So better that starting before that, I thought that okay, let's take some questions if you have, then in easy word we'll go. So this point whatever now I will teach, so we will now afterwards we'll stop that, and we'll maybe meet in the on Wednesday something in the afternoon time. So Wednesday you guys are how is your timetable on Wednesday? You guys are working, someone, Murli sir, you are working, no? I'm thinking to have in the morning, your afternoon time, having time, or then we have to then finally go on the weekend only then, if oh, okay, 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 no problem. Okay, okay, got it, yeah, no problem. Let's see what we can do with there, because week 2 is something more math, and this onwards the actual things now start, like we are now climbing. Yeah, yeah. Because now I will just hmm. Yeah, we'll go step by step. Yeah, we'll go, because yes, we'll do that. Uh, okay, so I hope now we will, because this next point is actually the point where we are now dealing with, as I mentioned, na? So we have the time complexity of d cube, like d cube. So remember, okay, this d cube, okay, this is very much important. The exam, the questions will ask like what is the time complexity of the PCA. So it's the cube of your dimension, okay, d cube. So what we now understood, that the main challenge in this is the eigenvalues calculations, because what is eigenvalue eigenvector calculations, they're taking more time. But if you increase the number of dimensions, obviously the values will increase. So but the PCA, we found that we are doing this kind of calculations with a value where a number of images are greater than the dimension, okay. But when your number of dimensions are greater than the images comes in this eigenphase calculation, what we have seen in the example phase detection, that time this is like a generic. This may come like I just gave you one example of phase detection, but this may come in the future if on another algorithms also. So you have to figure out some solutions. So that type of solutions, or that issue number one, the time complexity of d cube, we will try to work on that, where number of features d are too much greater than the number of images or number of input n, okay. So here here, so first, because this is little more or less math, but I don't want to feel you bore. So what we'll do, I will also explain its way how what we are doing, but you just need to first understood first point, okay. For example, we have seen that I will not now go to that the actual point, but the first generic point, okay. We know that there is one matrix, for example A is one matrix. The A is, for example, 1 2 3 4 5 6, okay. It is 2 cross 3 matrix, okay, 2 rows and 3 column. And in all the calculations, if you actually check the SVD and all, where we are converting the R3 or R3 dimensions to R2 dimensions. Like you are actually reducing the dimensions, you are changing that number of dimensions from 3 to 2. Okay, means here also you are doing some kind of a compressions in SVD. Okay, you are doing some kind of a compressions, you are reducing the dimensions. Instead of storing that many images, you are storing the less information, but that information will give you the complete information about your data set. It's not like you are just discarding something, you are just reducing that, creating new features in R2, which will give the complete flavor of your complete data set, give the complete information about your data set. Okay, so for example, this is one matrix A. Okay, so this is not a symmetric matrix. So what is a symmetric matrix? We know that symmetric matrix is something here. For example, if I just take a normal one, 1 and 3, 2 and 2. So symmetric matrix means this is diagonal matrix, this is diagonal elements, and these two and these two, if they are similar, okay, or there, if it's a 3 cross 3 matrix, 1 2 3 4, oh sorry, 2 4 5, and this is 3, and this is 5, and this is 6. If this is a matrix, this is actually the symmetric matrix, because these elements, these elements, these elements are same. Okay, and these are the diagonal elements. This is called as symmetric matrix. Okay, the point is here, if we have, like, I'm just giving you some background. Okay, we are not started with the actual point, but I'm just giving you some background here. So this whatever A matrix I have given, hmm, hmm, oranges, uh, uh, here this one to mean, no, I'm saying that the, if I'm just drawing, if I have some data, and if I'm just putting into the matrix form, so the values here, these will be the similar, like I am arranging the values in such a way that, or the matrix whatever I have arranged or created, the values at rows and these columns will be similar, like these diagonal. Okay, so something like Kij equal to, okay, so these variables, these, for example, these are like x1 features, x1, x2, x1, x3. So for here, yeah, so for example, he is a Murli. So Murli has 1 kilo of gold, 2 kilo of silver, and 3 kilo of bronze or something. Ashwin has 2 kilo of gold, 4 kilo of silver, 5 kilo of bronze. And here Preeti has 3 kilo of gold, 5 kilo of silver, 6 kilo of bronze. So if you see, these values are actually similar, like three, this diagonal, like here the symmetrical, why I'm saying symmetrical, because the diagonal elements are like water maybe, but the combi, these variable Kij and Kji is same, and where j is not equal to I, because see, j and I will be same means these elements 1 comma 1, 2 comma 2, or 6 comma 6, they are like same. But if they are not similar, but other element, this Kij, so first row second is second row first, like this, these elements should be the same. So if they are same, they are like a symmetric matrix. Okay, so we are actually coming to the point where this concept is important for our PCA. Whatever, now we found the first issue in the PCA, that the time complexity is cube of your d dimension. Okay, time complexity is cube of your dimension, means whatever operation you do, it is like the dimension, whatever d value it has, that the cube of this is your time complexity, this much time, or it is like this much time consuming. So you don't need to get something, this kind of a calculation, because eigenvector and eigenvalue calculation is very time consuming because of their time complexity d3. and you don't want to do these kind of calculations where d is huge than the n. So we have to find out some solution. To find out some solution, we are going to that point, but before that we are understanding the point, or we are understanding some normal concept which we will use into that solution of the our first issue. To solve some first issue, we are referring to one basic concept here, and that concept we are just checking in few minutes. We will do it, and then we'll actually go to the actual part. Okay, in the symmetric matrix, now what I have seen is what I have showed you is like A is not symmetric matrix because 2 is this is not like a square matrix. First of all, it should be square matrix, and it's not a square matrix. And also if you see this inside this also, like no, wait, okay, it's not the same, so it's not the symmetric matrix anyway. It's like different, it's not a square itself. Okay, so if I want to make it symmetric, what I can do? Any idea? If I want to make this one as a symmetric, what is the easiest way to make that A as a symmetric matrix? Or A's family should be the symmetric. Now A is not at all symmetric. I want to do something with A, make their combinations, do some kind of multiplication with A with some other to make their combination as symmetric. So what I can do here, okay, so what I can do in this case, if I do A into A transpose, so for example, if I do 1 2 3, because this is 4 5 6, this is A. Okay, what is this? 2 cross 3. Okay, A transpose is what? 1 2 3 4 5 6, 3 cross 2. So okay, this is 3 cross 2. So the final answer, if I just do this matrix calculation, so 1 4 and 9, so it should be 14 32 32 and 77, which is 2 cross 2. So you can now see that yeah, so if you see that 2 cross 3 3 cross 2, so I am calculating A into A transpose, which is now not 3 cross 3 2 cross 3, it is actually 2 cross 2, and it is symmetric. Okay, this is symmetric matrix. Okay, so this symmetric, and if I just do A transpose A also, if I do A transpose A, okay, which is nothing but first of all 1 2 3 4 5 6, which is 3 cross 2, 1 2 3 4 5 6, 2 cross 3. So I'll get some final matrix which is 17 22 27 22 29 36 27 36 45, which is of 3 cross 3. And no, this is something before our class I calculated, just to explain you. Here this is not I can do it, maybe I can write some code, but that is not useful for our demo, just to give the feel of how we can create any matrix to its symmetric matrix. So maybe some question will come if you are going for this interviews, and also how can you make one matrix as a symmetric matrix if it is 2 cross 3 or 3 cross 2 matrix, how can you do that? So you can just give that once you multiply the same matrix which is transpose, or transpose the matrix with and multiply with its own, then you will get the final output which is like the symmetric matrix. So this is what you can get the symmetric matrix. So okay, so what you found now here, this 2 cross 3 matrix, okay, that you created this here. Okay, this 2 cross 3 matrix, which is your A matrix, 2 cross 3, you converted its A into A transpose, which is 2 cross 2, okay, which is symmetric matrix, and A transpose A, which is 3 cross 3, this is also the symmetric matrix. Okay, and whatever A into A transpose you have calculated, this A into A transpose, so what is this? 14 32 32 70 32 and 77, what is this? This is nothing but these are your eigenvalues, okay, of these matrix, okay, eigenvalues, okay. And so I can just maybe write like this u1, u2, sorry, these are eigenvectors and vectors. Okay, and for this matrix, this is, what are these? This is also eigenvectors v1, v2. These are normalized one. Okay, v3. Okay, I need to then do this one. Okay, these are like you are just doing this total sum, and like you have to normalize that. You have to do the total sum and divide by each value. Like for example, if I am having 5, 6 and 7, so if I just calculate like what is this 13, 18. Okay, so you have to normalize, means 5 by 18, 6 by 18, 7 by 18, just to make sure that all are like having the same kind of ratio. But generally normalization where we do, yeah, means like 0 to 1 range, if it is something like this, na 0 to 1 range. So we generally do this kind of normalization in the deep learning. What we do, so whatever the image you are having, for example, you are having a big input image. Okay, like don't exactly consider that as one input pixel value. Okay, but something like you are having one multiplication like 432, one is like 4, and next multiplication is like a 38. And if you see these values, these are something not the exactly in the range, like one digit value, 3 digit, 2 digit, 5, 4 digit. So it's not like looks like same in the same range. And if you plot there, one will be here, one will be here, one will be here, something like this plot will come, for example. So what we generally do, like you have to normalize this value, so to bring it into the range of 0 to 1 only. So some will be 0.001, some will be 0.1, some will be 0.123, something, but they all will fill into this 0 to 1 range. And so that time it's easy to plot the graph, or that time it's easy to do the next calculation. Okay, so that's why you do this kind of a normalization. Okay, but this is something, the applications of that. But here whatever the vectors we are getting now, so this a into a cross t, here whatever I have mentioned you, a into a transpose, the symmetric matrix what you got. So these 1432, these are the normalized eigenvectors of this matrix a to a transpose. And for this also v1, v2, v3, these are the normalized eigenvectors. Okay, so what we call this one as, so what we call this a1 and a2 matrix here. So for example, a into a transpose, I mentioned that they are like sisters. Okay, for example, they are like a sisters. So you, one is your a, one is your a into a transpose, and one is your a transpose into a. So this is okay, so this is called as left side, they are at the left side. So that's why I mentioned them as a left sister, and this is your right side. um yeah, you mean to say u here, vectors, huh. So yeah, this is what these are the, yeah. So where we are going now, we are trying to go toward the SVD, singular value decomposition. So what SVD say that any matrix, whether it's symmetric or not symmetric, or whether it has high dimension, low dimension, different ranges and all, whatever matrix you are having, you can put the matrix into these combinations of matrix. Correct, you know that is SVD. Okay, okay. So see, singular value decomposition means any matrix, whatever maybe. Now I gave the example of this A, 1, 2, 3, 4, 5, 6. Okay, any matrix. Okay, any whatever maybe is range, dimensions. Don't care about that. The any matrix, you can decompose that matrix and put into these three matrices. These three matrices you can decompose that. So this SL is nothing but your U, this A is nothing but your sigma, and this A transpose is nothing but your V transpose, this value. Okay, So just means like consider whatever now we got now. You have one matrix A. You have one matrix A. It is 2 cross 3. It is not symmetric, and now you want to represent that non-symmetric matrix to symmetric matrix. And you have one somebody, or we learn that point in SVD, that any matrix, irrespective of its dimensions, irrespective of its range, or irrespective of its size, any matrix, whether it's symmetric or not symmetric, we can represent that matrix in this form. Okay, but how you represent? So what we did, instead of directly jumping to SVD, what we did, we created A into A transpose here. So what we did here, we created this A into A transpose. Okay, and we found that this 32 and this, we found that here, we found that these 32, they are same, and these are the diagonal values. Means this is symmetric matrix A into A transpose. And later on what we did, we also calculated A transpose T into A transpose and A, this value, and we found that these and these similar, means this is symmetric. Okay, so if I do, because now I am having symmetric matrix, square matrix, if I do these calculations, it's easy because all are now having equal dimension, m cross n, they are having like a similar dimensions here. Okay, like I'm not saying the actual calculation, basically 2 cross 3, but here what happened, they are now symmetric matrix, easy to evaluate later on for that, because in this A into A transpose, the values, these vectors, the column values, these are the eigenvectors. Okay, these are the eigenvectors, these are the normalized eigenvectors. So, and for this one also, these are the normalized eigenvectors, v1 v2 v3, they are the normalized eigenvectors of this A transpose A, and these are the normalized eigenvectors of this. But okay, how we can connect now A transpose A T, or A transpose A, or A into A transpose, how we connect all these three together? Because here I mentioned now this A transpose A and A transpose A, how we connect that? So we consider for this one, this is the left side. Okay, because this is what we did, this is left side. So we say that this is sister L, left sister, and this is right sister, yes sir. Just the example I am saying you, just to so it's easy for you to just remember what I am saying here. Okay, and what we have understood, like this, whatever the vectors, yes. So diagonal now I, yeah, so diagonal now, this sigma, whatever now this sigma, this is nothing but your diagonal matrix. Okay, so that sigma value, I will tell you what is this actually, the sigma value. Okay, so sigma value, this is important. Okay, so whatever now you got, so we are now able to represent A with like this, A into A transpose sigma A transpose into A. Okay, so what is this? This is what, this is called as your orthogonal matrix, or your, this is actually, if you, because these are like left side and this is right side, this is called as your left singular matrix, left singular matrix. This is your right singular matrix. Okay, left singular matrix, right singular matrix, and both they are like the orthogonal matrix, they are like orthogonal matrix, orthogonal, both are like orthogonal. And the sigma whatever we are now having, this is actually your diagonal matrix. Okay, this is diagonal. What sigma contain? Sigma, whatever the sigma we are having, this sigma contain your singular values. Okay, sigma 1, sigma 2, yeah, diagonally, and other than non-diagonal element will be 0. These values, singular value, these are like a sigma is like a singular value. This is called a singular value. Okay, and whatever other elements are there, whatever the other elements are there, they are 0. And you will say, okay, I got singular value. What singular value? What is the singular value? The singular values are nothing but, okay, the singular values are nothing but under root of your eigenvalue. So whatever the eigenvalue you are calculating, the singular values, whatever the singular value lambda, sigma 1, sigma 2, these are the square root of your eigenvalues. So you will say, what is this? Because I have two matrices, A transpose and A transpose A. I have two matrices. So the eigenvalues are different for that? No. Because, so here, whatever we have found that, you will get for A into A transpose, okay, the left side, okay, for you, whatever A into A transpose you are now having, you will get for this value some lambda 1, okay. And what is this? This is what, for example, if I just this is here, if it is 2 cross 3, this is 2 cross 2, this is 2 cross 3, this is 3 cross 3, their dimensions, okay. Okay, for here I will get, for example, lambda 1 and lambda 2, these eigenvalues. I will calculate A into A transpose, this covariant matrix, and then calculate the lambda 1 and lambda 2 for that. For A transpose, because how much is A transpose? A transpose is what? It's a U, which is actually 2 cross 2. Okay, what we found that, okay, here we calculated A into A transpose, which is 2 cross 2, this matrix, 14, 32, 32, 27. Yes. See, yeah, you consider this way, but for remembering you consider, but this not be always. But for example, you are reducing something, like you are bringing something R2 value, like some 2 dimension R2 to R3, okay, R2 to R3, you are increasing now the dimension. That time it will be reverse, right will be more and left will be small. When you are reducing something, when you are bringing R3 dimensions to R2, you are reducing the dimensions. That time U will be 2 cross 2 and V will be 3 cross 3, more bigger one. But for now you consider like this, like, okay, it's a 2 cross 2 here and this is 3 cross 3 here. For example, now you can see. So we will now reducing, because now we are considering compression in PCA, because singular value decomposition is helping in machine learning in all the basic compression technique wherever we are doing this data compression. So there basically we are going with the SVD only. So SVD is compressing the higher dimension data to lower dimensions, means, so whatever the Murli sir you mentioned, the generic thing is okay, like generic means you, for your understanding is okay, like the first is smaller and next is bigger, but in general this is like you are changing the dimension from D to N or N to D. If you are trying to do that, time you have to think about like where you should be smaller or you should be bigger, whether you should be 2 cross 2 or 3 cross 3, something like this. If you are going with the increasing the dimensions, then you have to make that instead of 2 cross 2 you have to think as a 3 cross 3. You have to transpose sigma also, so sigma will become 3 cross 2 that time. Here if I just go with here now, so it will become 3 cross 3, sigma become sigma transpose like 3 cross 2, and V become like this, and it become 2 cross 2, which transpose, something like this. Okay, so here the complete change will happen, but for time being, for your understanding, maybe you consider this this point, like 2 cross 2 and 3 cross 3. Okay, it's gone. Okay, yeah, okay. For basic example, it's okay, you can remember like this, 2 cross 2, 2 cross 3 and 3 cross 3. Okay, there is no problem. So as I mentioned, A into A transpose is 2 cross 2 as here. Okay, for this example 2 cross 2. So here what happened to V transpose, which is actually 3 cross 3, because we are doing A transpose into A. So you will get lambda 1, lambda 2, lambda 3, because 3 cross 3, so 3 eigenvalues. So if you check, because if you take some example and if you calculate that and if you see that the eigenvalues lambda 1 of A into A transpose, and here A transpose A, the first eigenvalues of lambda 1 of A into A transpose, and this A transpose A is similar. If you do this actual calculation, and if you see that with any example, you can take any matrix and you calculate like this, and you can see that the lambda 1 of A into A transpose or U is similar as lambda 1 of V transpose. Okay, this will be similar. Lambda 2, that the highest eigenvalue is like the maximum value. Okay, lambda 2 is the second maximum value of A into A transpose, is similar as A transpose A. If you see that, you can like get that both are similar, and whatever the remaining is there, because it's a 3 cross 3, so whatever remaining is there, it should be 0, means it will come as 0 only. So this eigenvalue of A transpose A, the last eigenvalue, will come as 0. So here what you found now, the matrix 3 cross 3 has more eigenvalues, and matrix A into A transpose has less eigenvalues. It has 2 eigenvalues, it has 3 eigenvalues. But and this lambda 1 and lambda 2 are positive eigenvalues. Okay, because these matrices are semi-definite matrix. Okay, so semi-definite matrix means what? Definite matrix means lambda is always be greater than 0, means eigenvalue is always be greater than 0. Semi-definite matrix means the lambda is 0 or greater than 0, so that's why they are positive values, 0 or greater than 0. So these non-zero eigenvalues, 0, I am not saying about the lambda 3, the non-zero eigenvalues of A into A transpose. Okay, this is important concept. I will write down here. Okay, now because this question will come in the exam, MCQ questions, so just you need to be okay. The non-zero eigenvalues of A into A transpose and A transpose A are similar. Okay, this is the basic thing you need to remember. Okay, so this point we will consider in our the issue number 1 of PCA. Okay, the non-zero eigenvalue lambda 1, this value lambda 1 of A transpose A and A transpose A, they are similar. Lambda 2 and lambda 2 of these are similar, so these are non-zero values. Okay, so the question may ask all eigenvalues of A into A transpose and A transpose A are similar, yes or no? So what will be our answer? Murli sir, what will be our answer? All eigenvalues of A into A transpose and A transpose A are similar. Is it correct or not correct? Yeah, so this is not correct. Yeah, because all eigenvalues of A into A transpose and A transpose are similar. It's not correct, because the A transpose A is having 3 eigenvalues and A into A transpose is having only 2 eigenvalues. So their eigenvalues are not similar, because you cannot compare lambda 3 with nothing here. In this is a lambda 3 of A into A transpose, which is like a 3 cross 3. Nothing is here for A into this 2 cross 2, nothing is here, so you cannot say that it is similar to nothing. So this is wrong, that what I mentioned. So the correct answer is only the non-zero eigenvalues, as I am dealing with lambda 1 and lambda 2 only. So only non-zero eigenvalues of A into A transpose and A transpose A are similar. Okay, in this case. Okay, so this is what the important point you should remember. And how we got that? Yeah, lambda 3 will be always be 0, because this is semi-definite matrix. So the extra lambda 3 or the next eigenvalue which is remaining, because this is less than the lambda 1 and lambda 2. Lambda 1 is the maximum value, lambda 2 is the second maximum, lambda 3 is the lowest one. So because it's a 3 cross 3, that's why I'm saying if it is a 5 cross 5 means lambda 5 will be the maximum lowest one. So the lowest eigenvalue is lambda 3 here, and that will be 0. That if you calculate that will come as a 0. And if you want the singular values of this one, if you calculate the singular values, okay, which is nothing but sigma 1 is equal to under root of lambda 1 sigma 2, which is nothing but under root of lambda 2, and sigma 3 is coming as 0, because the matrix, whatever the matrix you will calculate here, so whatever the matrix you are now having here is nothing but sigma 1 0 0 0 sigma 2 0. So this is your sigma for SVD calculation. Okay, you are having only sigma 1 and sigma 2. Sigma 3 is nothing, it is not there. Okay, because it's a 2 cross 3. Only sigma 1 and sigma 2. Sigma 3 is 0 because there is no lambda 3. So that value has to come as 0, and that will come 0. Other than this, because this is like what? This is this sigma is actually the diagonal matrix, and other u and v are the orthogonal matrix. And if you actually try to see, like, I don't want to go into the SVD composition, but in SVD what happen if some matrix is here, na? So for example, if there is some because u means like the orthogonal matrix will firstly rotate your object. If there is some object here, okay, there is a cube, so what it will do, once I do u into sigma is what? It's actually a reducer matrix, or 0 1 0, for example, if I'm taking like this. So what is happening? X, y and z. So z is this dimension is 0 in this case. So the z dimension is 0. So what it is doing, it is now multiplying with the u into v. Okay, so whatever the z is 0, so it will convert that to only x and y. If I just plot it now, it looks better, but I'm not able to now show that plot here. But here, what in first case what happened in u, sigma and v in SVD, and this is extra information I am giving. It's not like you don't bother about this, but extra information. Firstly, whatever the image you are having, any object, any human face or any picture camera image you are getting, in that one, if you are converting that normal A, if you want to put that image, like the photo is of this person, okay, and the person is having something, he is running or he is jumping or something, okay, he is jumping something like this. And if I want to if I want to put that photo, so what it will do, if I want to put that photo, so instead of directly plotting A, just for showing you what I am doing, I am firstly using this u is like your orthogonal matrix. It will first rotate that photo, it will first try to rotate the photo, means it will, if the person is something like this, it will do it just rotated the photo, like the photo goes like this, okay. And then what E will do, it will reduce the one dimensions, like if it is 3 dimension, it will reduce to 1 dimension, because for this example I took this z is 0, and it will stretch that, okay, 1 and 0, it is now stretching. So it depends upon your u, value, what u is having, for example 5, 0, 0, 3, and what is your sigma is here 1 0 0 0 0 1 0. So what this multiplication do, so whatever now you are having this 1 0 0 1, so 5 is along the x-axis, so I am now stretching that person's face like this, okay, and 3 and this y directions, okay, so I am now stretching his face something now like this in y direction, in this x direction, this is x direction and this is y direction. So I am making it large. With this multiplication, this happen like this uv, and once this uv done, v transpose, so v transpose is once again it is rotating back to its original shape. I am not good in drawing, and this is not exactly the correct example, but this is what the now, and if you see the actual A, the A will be also looks like the same, and this is what the your multiplication of u sigma v transpose will also give the same. So here what we are doing is, like, firstly you are rotating, then stretching along x and y axis, and afterwards you are multiply once again you are rotating it and bringing it to your actual position, or the required position. If you actually see these singular values, no, it will calculate the singular values in 3 dimensions. If I get the singular value sigma 1 here, sigma 2 here, huh? So what happened is it's stretching. It's just firstly rotation means it will bring the sigma 1 like this, sigma 2 like this, and then it will stretch along this direction, and finally it will because this is first position is here, okay, and then second position is rotation here, rotation and stretching, and then third position is once it comes to stretching, because it's stretched now, it's not like the same here this much, it's stretched now. I think maybe they like this stretch, and this is now put like this or rotated as per the v direction. So it is now like this. So actual image looks like this. So it's not that much important for you, but this is what SVD do. Firstly the rotation, stretching, and then once again rotation. That SVD do like this. But this is just the extra information. For example, what happened like SVD's applications. If I want to plot something, if the camera image is there and you want to rotate that image, like you are having Adobe photo filter, Adobe tool, where you are doing some visual effects into your photos or videos, or you are like editor and you want to do something like a rotation effect, then how you can do the rotation? Maybe you can just click on that and it will rotate, but behind that the image looks, behind these operations do, whatever the rotations and whatever the stretching operations are happening here, behind that your simple click, the algorithm will work and algorithm run, and it will rotate your image, flip your image, right left, or like you are mirroring your image, whatever the camera has so many effects na, like right hand looks different, left hand, like you are mirroring your photo in your mobile, or when you are editing your photo videos, then you will do some kind of effects there, or in the Instagram and all people do use lots of effects. So these kind of effects you want to do na, so these effects had done mathematically like this way, what I have just mentioned you, this whatever the effects you are doing. So nobody will simply just do that, but if you want to do, or if you got some image which is showing, if you are having, for example, you got the photo of your Mars, okay, but your camera, because your orbiter is just rotating in the Mars atmosphere, it gets some photo, but it doesn't know that whether the photo, he just want to capture the photo, the photo is like tilted or having different angle and all, but when it come to your station, you don't know, the photo doesn't look good, and then what you say that, oh, the photo doesn't look good, what you will do, you will just rotate the photo, you will do some kind of a calculation, you will stretch the photo, if it is smaller you will enlarge the photo, or you will zoom in, zoom out the photo, so it will looks proper, and it will be like for your next future calculation, or your whatever the decision you want to take, that time you have to do this pre-processing, these kind of operations on the photo. So for that reason you have to do these operations, like whatever I mentioned in SVD, first rotation and then stretching along the x and y axis, and once again rotate it to put it like properly. So if you just simply use SVD, because in the Python libraries, if you directly call SVD function, it will directly give you the proper image output, stretch one, proper whatever expected image what you want. So it will give the output to view you as per your request. But that is like applications of the SVD. But what SVD internally do is like rotation, stretching, and then once again rotation. 3 operations it will do. For first operation is orthogonal rotation is by U, and next stretching, whatever stretching along x or y axis, it by sigma, and the final is by V transpose, that is once again rotation. So 2 rotations and 1 stretching will done in the SVD. So this is like extra point, but we now we will not now go the next point, we will stop this point only, but this is the basic point, will come into the picture in the next session. So what we understood from this, from the SVD is that you are having one matrix called as A matrix. So we took an example of A is a 2 cross 3 matrix, and you are just representing the 2 cross 3 matrix. You are converting that matrix to the symmetric matrix by using A into A transpose or A transpose into A. Okay, and you found that A transpose and this matrix, if I consider this as a singular value decomposition, how we can represent? So A into A transpose is nothing but your U, and A transpose A is nothing but your V transpose. Okay, and sigma is nothing but your eigenvalues. But you said that A into A transpose has some eigenvalues, and A transpose and A has some eigenvalues. But if we actually calculate that eigenvalues, both will be similar. The eigenvalues of A transpose A and A transpose A, the non-zero eigenvalues will be similar. Okay, this point is very important. The questions will come into the exam. The non-zero eigenvalues, so you just remember non-zero, I am saying non-zero eigenvalues of A into A transpose and A transpose A are similar. Okay, every time. Okay, and number of eigenvalues of A transpose A are greater than number of eigenvalues of A into A transpose, because you have seen it's a 3 cross 3, it has lambda 1, lambda 2, lambda 3, which is greater than lambda 1 and lambda 2 of A into A transpose. So this is important. So you have to remember non-zero eigenvalues of A into A transpose are similar, and the number of eigenvalues of A transpose A are greater than A into A transpose. Okay, so this is the point which we'll use in the issue 1 solution. So whatever the issue 1, so PCA has the two issues. First issue is for eigenvalues and eigenvector calculation, it is taking too much of time because of time complexity is the cube of your dimension, d cube. So we can't do anything with the d cube operations. So what we want, we are thinking about a way that instead of doing d cube calculation, see what happened, we are doing eigenvalue calculation or eigenvector calculation. Means you want w value, correct? You want w value means eigenvectors, and eigenvectors is calculated by using this covariance matrix with d cube. But you are trying to figure out another way where you are calculating eigenvectors, that's fine, but without using the d cube, without using the cube of your dimension like d. So I don't want, I'm not interested in cubing this much of time complexity d cube. So if I'm avoiding that d cube, you do maybe n cube, that's okay, but don't do d cube. So but how we can come to n cube? So that is the way that what we will learn now in solving the issue 1. And when I'm giving the solution for issue 1, so there I'm using this logic. That logic is, or that normal statement of the matrix, because this is very important statement. So it's like we can prove it also, that what I have just showed you, that A into A transpose having the same eigenvalues as A transpose into A, the non-zero eigenvalues. Okay, they are like a similar, lambda 1 of both are similar. So this is what the reference for solving the issue 1 of your PCA points. Okay, so we'll check that point on Wednesday session. I thought we'll go today, but it's not good to go today because this is the something math things, and I don't want to you guys will bombard more on math, but this is what important point. So just remember the non-zero eigenvalues of A transpose A and A transpose A and A transpose are similar. Okay, so we'll now stop at this point. So we'll see on Wednesday, we can take, maybe because I also need to do other things. So Wednesday I will do the things as early as possible, and I will, because I need to also go to office. So yeah, that's fine. Okay. I feel that is also good option. But okay, Saturday we can do it. That's not a problem. Uh, but then, okay, I thought our uh, yeah. So I thought like Wednesday and like alternate days if we take, then we'll do it on Saturday also, but that the I like, see what happened now, the points are too many mathematic points, and if I take 3 hours of math means you will not understand anything. So if I just divide something like 1 hour or 1.5 hour sessions, then in 1 week we can finish with proper understanding of the mathematics explanation. Okay. Otherwise, we'll see on Wednesday what we'll do. We will see. Um, 1 second. Let me.